Done. All right, everybody. Hey, good to see you. Thanks for coming to class. I hope that you're having a good start to your day. I hope that you've what you call it um adjusted from the cold temps. You're good now. Um, I have a couple of announcements, and I'm gonna write those down. Um, at the moment on your Canvas page, you have a total of four quizzes that are open. Those would be quizzes 1.3, 1.4, 1.5, 1.6. All those quizzes are going to be due Sunday, the 26th at 11 p.m. That's quizzes. You've also got two activities that are going to be due that same time, Sunday, the 26th at 11 p.m. Those activities, I believe that I've got those up now. You need to submit those, and please submit those as a PDF. If you take a picture, copy and paste it into a Word or Microsoft Word document or a Google Doc, and then export that as a PDF. Alternatively, there's a handful of other pieces of software that you can use to put together a PDF. Um, all told, this semester we're gonna have somewhere in the order of like, I think it's probably gonna be like 40 plus quiz grades. And so I'm actually gonna drop six effectively. Um, Effectively 2 weeks worth of quizzes will be dropped. Um, and so as a result, unless if I make a mistake like I did last week where I didn't finish all the material that I wanted to, um, then I'll extend a quiz date. But if you miss or something like that, um, I'll communicate with you and everything. But I don't extend due dates just because I dropped six quizzes. So if you missed last week's quizzes, don't worry about it. You have three more that you can still miss and not impact your grade really. Um, then I think that's about it. I did adjust all the times, so if you have accommodations for additional time on your quiz, I've got that worked in, so we're good to go there. And then while we're here, um, I've got some poll questions, but those are going to be for the second PowerPoint that I open up. And I just want you to know that one of the things that I like to do and have done historically, and I'm cool with doing today, is if either every person who answers the poll question gets it right, or every single person responds to the question, I usually like to add like a bonus point to the upcoming exam. So just kind of incentive to like stick around and answer them. Or I've never had this happen, but I suppose you could all coordinate and be like, hey, nobody answer it. Just one person answer it. He said 100% of the people answer it, get it right. We're good. All we need is one person to get it right, and then 74 other people just be like, anyway. Um, okay, so amino acids. These are a pretty big deal, a pretty big part of biochemistry, and in particular protein biochemistry. Um, so we're going to go ahead and get cracking. This is effectively your amino acid backbone. Now, one of the things that I want you to recognize about this, I stand corrected. I do have a poll question almost right away. Um, One of the things that I want you to recognize about this is that this molecule right here has a carboxylic acid, and then the naming convention for the first carbon coming off of that carboxylic acid is to identify this or refer to this as the alpha carbon. So if ever you hear about like a beta carbon or a gamma or a delta carbon, that's in reference to that carboxylic acid. Okay, so that's another reason that sometimes when you talk about amino acids, you'll sometimes hear them referred to as alpha amino acids. So there's a handful of different terms that you might want to just be adaptable to. The term that I like to use more times than not Is protein ogenic amino acids? Some people will say alpha amino acids. Effectively, we're talking about the same group of molecules, but I like to go with proteinogenic because that's kind of my way of communicating that what I'm interested in is how these things are put together to make a protein. So off of our alpha carbon, we have a couple of things. One, we've obviously got our carboxylic acid. We've got a singular hydrogen, an NH3, and an R group. Now, this R group, that's your variable part. That's the part of the molecule that makes one amino acid different from the other. And that's significant because what that means is every single amino acid has this same backbone. I always like to draw, and this is something that I like to say right off the bat is I like to draw them fully protonated. Um, that honestly, it kind of stems back to when I was a student learning ionization. I struggled with identifying or I struggled with the relationship between pH and pKa. And so what's always been easiest for me is to say, I'm drawing this molecule at a pH of, I'm just going to say 1. And, you can say 1 and infinitely low pH, whatever you want to say. But I'm drawing this molecule at such a low pH that every place that a proton can go and this molecule will remain intact, it's going to go. And so here what I have is my molecule where it is fully protonated. Now, before I pull up the poll question, or the first poll question, um, what I want you to recognize about this and what I want you to think about with respect to this molecule is I will ask questions about charges. And so I'll ask a question like, what's the charge of this backbone? And I'm not, trying to throw you off or anything like that. Positive, neutral. Okay. So if I look at this molecule at a pH of 1, this molecule has a charge of +1. Now, with that in mind, let's go ahead and tackle our first poll question. How many ionizable protons does the molecule on the screen have? 0, 1, 2, 3, or 4? I'll give you another couple of seconds, maybe 10 seconds. 5 seconds. We got 70 answers. Okay, I'm gonna go ahead and stop it right there. Okay, so there were contributions for all of them. Um, and one thing that you know, I always try to look at the answers, look at the responses that people give, and I don't know if this is a good or a bad thing, but I always try to explain or think about, okay, why would somebody answer this? And so whenever I see the word protons, one thing that I want to kind of clear up is a proton or a molecule being protonated doesn't necessarily mean that it or a functional group has a positive charge. Now, the correct answer for this question is 2. The 2 that are ionizable or that basically can be lost are right here and, well, really any one of these on this nitrogen. So we've got our carboxylic acid, and one kind of tell or one sort of um, clue is whenever you see a pKa, that's a good indication that you got 2 ionizable groups. So effectively, we've got a carboxylic acid, which it's important to remember carboxylic acid can be neutral or negatively charged. And then this N termini can be positively charged or neutral. So the correct answer for that was two, and those are two groups that can be protonated or deprotonated. Now, to get a little bit of a flow of what that looks like, here what we have is, again, our molecule when it's fully protonated on the far left here. It's completely protonated. The carboxylic acid, also known as the C termini, and then the amine on the N termini, the amino group, is also fully protonated. Now, this is effectively a schematic that shows this molecule going from its fully protonated state, where we're at, I'm going to go ahead and say at that low pH. Then, after that, I'm going to lose that proton. Okay. Where did I lose that proton from? Well, I lost it from my C termini. Now, I'm including this language intentionally. N termini and C termini, those are the conventions that we use to talk about proteins and amino acids. The N termini is typically drawn on the left-hand side of a molecule, or typically on the left-hand side of the drawing, and then the C termini on the right-hand side. So my C termini gets deprotonated. Then after that C termini has been deprotonated, I can deprotonate my N termini. Okay, so effectively my backbone can go from a charge of +1, oopsies, +1 to neutral to -1. That's the range of my backbone. Now, one thing that I want you to recognize is that every single amino acid potentially has, or sorry, not potentially, every single amino acid has that same backbone. So effectively, what that means is every single amino acid is at very least a diprotic amino acid because it has two protons that it can lose. Now, there are some amino acids that are triprotic. There are some that remain diprotic. And those that are triprotic, what makes them different from their diprotic counterparts is this R group right here. Is that R group going to have an ionizable functional group? We'll introduce those in just a little bit, but it's important to know I think the parameters and the boundaries of what that backbone can possibly look like. Because if you understand that, that's going to put you in a really good place. Like if you were ever trying to think about, okay, how can I draw a titration curve for an amino acid? Well, I mean, if this was a question that you were asked on a, worksheet where you know, wrote down on it, you'd be like, okay, well, I'm drawing a blank, but I know every single amino acid is at least a diprotic acid. So it's got two ionizable groups. Some will have three, but at my base, it's going to have two. So I'm going to go ahead and draw a titration curve that looks a little bit like this with two horizontal regions. Okay, so this titration curve here is I don't want to toot my own horn, but a pretty fantastic rendering. And yes, I did use the word rendering because it makes me feel fancy. Rendering of a titration curve for a diprotic acid. Okay, so there's a little bit of language that I want to bring back. Diprotic acids. Okay. Um, two ionizable groups and alpha carbons. So our alpha carbon, I always just, my alpha carbon's in the middle. That's kind of how I draw it. And then to the left of my alpha carbon is the N termini. To the right of my alpha carbon is my C termini. So all that is good terminology that is going to be really helpful as you work through understanding amino acids and peptides and proteins. Okay, now this is where things can get, I don't know if I would say complicated, but um, a volume of information or the load of information is about to go up quite a bit. And this is a place where I know whenever I was first taking a biochemistry class, it was like, oh man, you got to know the three-letter codes for your amino acids, oh, this is brutal. And, you know, it's tough. But um, these three-letter codes are the identifiers for our 20 proteinogenic amino acids. Now, if you look in some textbooks, you might find 22 proteinogenic amino acids. Um, but I'm sticking with 20. And the reason for that is the other two that are your less common are so much less common. I apologize. Um, they're not found in human beings, they're not found in mammals. So they're a very, very small factor. If I remember correctly, selenocysteine might be found in mammals. I can't remember. I always get there's two other ones. I want to focus on these 20 proteinogenic amino acids. Okay, so the table in the lower right-hand corner is where you'll see the names. The names as well as a three-letter code identifier. Now, I bring this up because I really like, kind of the story. I like to say this from time to time to my wife, which she kind of rolls her eyes at, but I guess that's part of relationships. Um, I was a history minor as an undergraduate, and so um, that's that's really fun in games to mention. But then when my wife will say like, "Oh, well, we can ask our resident history minor, Joel, what do you have to say on the subject?" And that's when I'm at a loss. At any rate, I think really whenever it comes to history, I like stories. I like people's stories. And so these three-letter codes, if you look at the three-letter codes, there are quite a few of them. You can look at aspartic acid. The three-letter code for aspartic acid is ASP. Okay. You flip through a couple more of them, and there's kind of a pattern of, well, it's the first three letters of that name, of that amino acid's name. There are some that don't align with that. This paper right here, and I don't know that it's a paper, more of like a almost a press release of sorts that was issued in 1966. And it was this paper that established, like, hey, here are the guidelines that we use to identify proteinogenic amino acids, the three-letter code rules that we follow. And, we're going to follow these, and here's the rationale why. I like to bring this up also because one of the people who's pretty, I would say, what's the word? No, I'll just go with essential. Pretty essential to it all is this woman here, Margaret Oakley Dayhoff. I like to bring her up because her story is that she was a PhD student and doing, I think it was protein folding dynamics. So she was doing lots of really intense math and statistics on how proteins fold back in the 1950s and 60s. And to me, simply someone being in the field of bioinformatics in the 1950s and 60s is like, I didn't think that the word bioinformatics existed. And maybe that word hadn't really been established, and maybe that wasn't the term that was used. But I always thought that was pretty awesome because, I mean, I didn't get introduced to computers until the 80s. But she was working on computers and basically using these calculations. And one of the things that she recognized was if you're listing a protein sequence, it's really burdensome to list out the entire name of every single amino acid. To list a peptide as starting at the N termini, aspartic acid, methionine, glutamine, glutamic acid, so on. She was like, this stinks because it produces problems whenever you're actually looking at your data. And it's just one huge barrier to kind of completing things. And so she kind of was seminal in and important in developing both the three-letter code scheme and the one-letter code scheme. Here, what we've got is our one-letter code scheme. And if you look at most of these, like ALA is the three-letter code for the amino acid alanine. The single letter code for that is A. And so This paper that was published in 1968 kind of brought back like, okay, well, three-letter codes have this, one-letter codes have this. Why? And the rules that were ultimately established. In many cases, it's as simple as, well, let's use the first letter of that amino acid. But what about when we encounter something like glycine, glutamine, and glutamic acid? All three of those amino acids' common names start with the letter G. What do we do? And it seems a little bit silly, but the selection of the single letter identifiers were either the first letter, or in some instances, they were using someone's like phonetic pronunciation of the name. For example, GLN and Q. Well, GLN is, I'm going to flip back. GLN is this right here, glutamine. How did you end up with Q? Now, as it turns out, this is kind of a helpful thing for people learning amino acid structures and names. It got Q because the phonetic kind of almost really tough pronunciation of this name, people were saying Q-tamine. So Q. And I know whenever I was an undergraduate, we talked about, okay, what's a good mnemonic for this? Well, you could say that it's the cutest amino acid. You could, if you wanted. At any rate, so these are our single letter codes. Those single letter codes are either based on what's the first letter of the name, what's a phonetic pronunciation, and then also some of them were based on, well, we gave this like aspartic acid and glutamic acid. Oh, I see something in the chat. Sorry. Thank you. Thank you. Thank you. Oh. Um, so aspartic acid and glutamic acid have the pattern of D and E. In just a moment, we're going to look at um, asparagine and glutamine. Those two amino acids look very similar to aspartic acid and glutamic acid. So that's kind of the background of the nomenclature. Now, what I want you guys to know, I want you to be able to identify one letter and three-letter codes. I want you to be able to go back and forth from one letter code to three-letter code to full name, and then from full name to three-letter to one letter, and so on. In addition to that, we're going to look at the structures. For this class, there will not be any sort of questions on your exams where I ask you to draw these structures. Will you need to be able to identify them? Absolutely. Now, with that, let's go ahead and proceed. So there we go. That's the big deal. Now, amino acids can be classified in a number of different ways. And if you think back to any biology class that you maybe have ever taken, classification and organization is like everything in biology. Um, Amino acids can be categorized in numerous different ways. For example, you could classify these structures based on, are these amino acids dietarily essential or non-essential? Do we have to get them from our diet, yes or no? You could also ask, what's the fate metabolically? Is this something that's going to be broken down into sugar and make its way into glycolysis? Is it going to make its way into the citric acid cycle? Then you could also do things like, oh, well, this side chain or this R group contains oxygen and these don't. I apologize. So there's numerous different ways that you can classify amino acids. Now, it depends on where your kind of career path and study with this class takes you. If you go in the direction of nutrition, chances are you're going to look at essential and non-essential. Similarly, if you look at where is that non-essential amino acid coming from? What's it being synthesized from? So there's tons of different ways. I think the most effective way is just to make it, take these 20 structures and split them right down the middle. And just ask the question, is the side chain polar or non-polar? Now, here what we have are our polar amino acids. Starting in the upper left-hand corner and going down, we have side chains that all have hydroxyl groups. Now, anytime you look at an amino acid, it's important to be able to kind of pin where that alpha carbon is. Alpha carbon, alpha carbon, alpha carbon. Okay. Then what I'm going to do is say, okay, what comes off of that alpha carbon? Well, here is CH2OH. That is serine. That's all that serine's R group consists of. Now, I found both in my teaching and my experience as a student, it's very tempting to look at this and say, okay, well, I'm just going to memorize, I'm going to come up with a great acronym for all of these amino acids that are my polar amino acids. But what I think is really helpful and really powerful is to look at that side chain and take a pause. Okay, we've got X over that, CH2OH. Okay, why would this be polar? Well, what do we know about that oxygen? It's got two lone pairs of electrons. Okay, those lone pairs of electrons are going to have some, um, basically a dipole moment there. So that's where our polarity is coming from there. Threonine. Well, threonine's got a hydroxyl group right there. Tyrosine, hydroxyl group right there. So I think that it's helpful to go ahead and familiarize yourself with those structures where you can identify here is my OH group. Now, serine, threonine, tyrosine all have hydroxyl groups on their side chains. Then we've got asparagine and glutamine. We've also got this guy right here, which is cysteine. That yellow atom right there, yellow is the chemist common color for sulfur. So cysteine is a sulfur-containing amino acid or a side chain with a sulfur. Okay, now I'm going to draw a big line between those six and these five. The reason that I'm going to do that is because if we look at these side chains for lysine, histidine, and arginine, one of the things that I want you to recognize is boom. Hmm, hmm. These are all positively charged R groups. So these are known, lysine, histidine, and arginine are our polar positive. Now, a fair point is to recognize, well, I'm showing you these amino acids at a charge at a pH of 1. Lots of things are going to be positively charged at a pH of 1. But the significance is that these polar positive are positive at a neutral pH. And I'm specifically looking at the R group. I don't care about basically the backbone. I don't care that the backbone has two ionizable groups. I care about two ionizable groups. I care about the R group. Then below that, we've got aspartic acid and glutamic acid. Aspartic acid and glutamic acid. Okay, we've got CH2 and then a carboxylic acid. CH2, CH2, and then a carboxylic acid. The difference between aspartic acid and glutamic acid is that glutamic acid is only one carbon longer. Both R groups, however, have carboxylic acids. And a carboxylic acid, whenever it is fully protonated, is going to have no charge whatsoever. But as an acid, it's going to have kind of a low pKa. And whenever these groups right here and here get deprotonated, what does that tell us about the charge of these two R groups? It's going to go from neutral to what? Add it to the chat if you feel comfortable, or I'm just going to... Exactly, it's going to be negatively charged. So these two amino acids, aspartic acid and glutamic acid, are our polar negative. And of course, that negative is similarly based on it being negative at a neutral pH. Now, if lysine, histidine, and arginine are polar positive, aspartic acid and glutamic acid are polar negative, well, the other six are polar, but do they have a charge? No. These are commonly known as our polar uncharged residues. Okay, so that's 11 of our 20 proteinogenic amino acids. I like to approach the polar amino acids first, because whenever I do that, then I can look at, you know, taking this entire cake and biting a small piece off and processing that. I can say, okay, well, I can commit to memory the structures, the three-letter and the one-letter codes of my polar negative residues, because that's only two. Once I've got those down, then I'm going to go to my polar positive residues. Now I've got three more. Once I've got those, I've got a total of 5 amino acids in my book. Then that gives me my six remaining polar uncharged. Well, what I'm going to do is I'm going to tackle serine, threonine, and tyrosine. Those are polar uncharged, and what makes them uncharged is that hydroxyl group. Okay. After that, I've got asparagine and glutamine. If you look at the asparagine and glutamine R group, one thing that you'll notice that this little functional group here is the same here and here, respectively. Then last but not least is cysteine, which has a sulfur. Okay. So when it comes to understanding your amino acid R group structures, it's really best to be able to break it down into smaller pieces, understand it, move on. Understand it, move on. So we've gone from 20 proteinogenic amino acids down to polar and unpolar, and then we can kind of peel back the onion of the polar residues and look at those individually. So now we're going to go on to our 9 remaining non-polar residues. Now, the non-polar amino acids are a little less interesting. And I feel fine saying that. They're kind of boring. Do you need to know them? Yeah. Do they contribute to protein structure? They absolutely do. But if you look at most of these R groups, well, it's lots of hydrocarbons. Maybe there's a ring, an aromatic ring. Okay, cool, neat, fun. Woo! But there's not really much you can use to like separate them off. Um, you can look at proline and say, oh, well, proline kind of has an R group that goes back on itself. Well, that's weird. And then let's see what else. We've got tryptophan, which makes a double ring structure, and that's cool. And the single letter code for tryptophan is W, and its structure kind of makes a W. So that's like cool, I guess. Methionine is our other amino acid with a sulfur. The reason that this is a sulfur-containing residue and it is classified as non-polar is because beyond that sulfur, we've got a CH3. So those are kind of that's what we've got with respect to our non-polar residues. Um, I think that also it's worth noting, I'll share my candid preference, and I think the polar residues are much more interesting because they have R groups that will participate in different types of interactions. Non-polar residues are pretty much limited to the hydrophobic interactions. That's not to say they don't have any sort of interactions, but that's kind of where the king's ransom is. That's a great question. I call them residues because that's the kind of conventional term whenever you talk about them as a part of a protein. So thank you for asking. I'm sorry that I started using that and just moved on. Um, so yeah, they're just residual building blocks. Okay. Now this wraps up the end of our first PowerPoint. But what I'm going to do is first, or sorry, is does anyone have any questions? Okay. Let's see. We've got another presentation. Jump ahead. Okay. Um, this presentation, let's see. I can go Pulp Fiction on this one and start at the end. Okay. What is the best way to marginalize the non organize or marginalize? Organize. Okay, that makes more sense. Because I kind of marginalize them because I don't think they're very interesting. The best way to organize, I think, would be to basically go through and say, kind of categorize them based on. Actually, I can jump back real quick. I would categorize them based on does the R group have anything interesting to write home about? And whenever I look to answer that question, I can say, okay, well, um, I'm going to categorize or group together glycine, valine, alanine, isoleucine, and leucine. I'm going to group those five residues together. The reason that I'm going to do that is because four of those residues have nothing but hydrocarbons. The fifth of those, glycine kind of stands out because it doesn't have, as its alpha carbon right there, it doesn't have anything on the side, any sort of side chain. It doesn't have a carbon coming off of it. Now, to dig into that slightly deeper, one thing that I want you to know about glycine is that this is an amino acid that is not chiral. Because notice how glycine, that alpha carbon goes to hydrogen. It goes to two hydrogens, two individual hydrogens, so two identical groups, and then the N termini and C termini. Every other amino acid is chiral. Glycine is not chiral. So I look at those five together. And then that leaves me a group of one for methionine. And then proline I'm going to keep kind of on its own because of the fact that the R group covalently bonds to the N termini of proline. Then that leaves me tryptophan and phenylalanine, which we'll see in just a second, but both of these have a six-membered ring. Tryptophan has a six-membered ring and a five-membered ring. So those are the ways that I would categorize them or kind of organize them to like break them off into smaller pieces. Does that help? Okay, cool. All right, great. Now, okay. So like I said, I'm starting at the end of this presentation. I'm kind of going to work backwards. So here what we have are example R groups. Um, these R groups for right here. Let me write this out. This is one of the things that we are interested in when it comes to amino acids. They're not just the building blocks of proteins, but they're chemical compounds. And those compounds are going to change. And those compounds can interact in certain ways. So here what we have is tyrosine. And then this right here would be probably asparagine. Um, add to the chat, what type of interaction do you think might take place between these two amino acids? Hydrogen bonding. You're absolutely right. Hydrogen bonding is more than likely going to take place of these because, well, that nitrogen can be a hydrogen bond acceptor and the oxygen can be a hydrogen bond donor or vice versa because that nitrogen's got Well, actually, the nitrogen chances are is going to be acceptor. Now, these guys up here, it's a bunch of hydrocarbons, hydrophobic interactions. These guys down here, this would be great for ionic interactions. So whenever you look at any sort of amino acid R group, think about, okay, what sort of interaction could this have with another amino acid? How's it going to interact with its environment? I think that's an important part whenever you're classifying your amino acids. And I hope that that will bring kind of more value to classifying some amino acids as polar residues or polar amino acid residues, because those polar residues, they're going to have some sort of, well, an ionic or a hydrogen bond interaction. Whereas your non-polar residues, no disrespect, but it's a little bit boring. Yep, hydrophobic effect. The end. The last one, this would be, let's see, H bond, hydrophobic. And last but not least, this would be an ionic. And sometimes you'll see that as a described as an electrostatic interaction. But that's kind of the big three there. Then there is one particular amino acid, one of the two amino acids that has a sulfur in the side chain. The two amino acids with sulfur are cysteine and methionine. Cysteine has a thiol, or you might hear it referred to as a sulfhydryl group, an SH. Well, that can undergo an oxidation reaction, in which case those thiols can form what's known as a disulfide bond. Now, a disulfide bond is an example of a covalent bond. And that covalent bond between those two sulfurs, well, that covalent bond is not going to care about a change in the pH. It's not going to care about the environmental conditions. In order for that disulfide bond to be broken, it has to be reduced. That is a example of a covalent interaction that only occurs between these two amino acids, cysteine and cysteine. It's not going to happen between methionine and methionine. It's only going to happen between cysteine and cysteine. So let's go ahead and answer a poll question. I'm going to switch the slide so I'm more sly about that. Let's see if we can get 100%. Nope, too late. Yeah, you got about 5 more seconds. I think we can get all 76 people to answer. If we do that, it's a bonus point on the next first exam. One freebie. We got 72 people. I can give you 10 seconds, 73. 5 seconds. It didn't happen. But the important part was that the vast majority of you guys gave the correct answer, covalent bond. Those two terms, keep in mind that a disulfide bond is an example of a covalent bond. So all disulfide bonds are covalent bonds, but not all covalent bonds are disulfide bonds. Okay, so one other property of some of our amino acids is we've got, I'm going to label here on the far left, this is tryptophan, TRP, that's the three-letter code for that. Next is TYR, and then next is PHE, phenylalanine. These are three amino acids that will absorb some light within the UV range. Now, this is really helpful because it gives you a way to detect protein. So if you use UV spectroscopy, you can set a light or set a light to have a wavelength of 280 nanometers and shoot it at a sample. And if that absorbs some light, that is an indication that you have these amino acids. And chances are these amino acids, if they're in anything, it's going to be within, within a protein sequence. Now, so that's a good way to detect proteins. Okay, jumping back. Amino acids. Every single amino acid is chiral except glycine. The most common forms of our proteins or of our amino acids are our L amino acids, as opposed to our D amino acids, levorotary and dextrorotary. Later on this semester, we'll talk about sugars, and sugars form the D configuration more so than the L configuration, or naturally occurring sugars do. Okay, now this was where I wanted to go with respect to kind of ionization. We're going to go back to this isoelectric point. So isoelectric point here, iso, same, electric, okay, point. So this is on a titration curve. This is a point where um, a molecule has a net charge of 0. Okay. Now, one of the important parts about this is that this is a net charge. So what that means is that you're basically down to a molecule with one positive charge and one negative charge, and they effectively cancel one another out. So when a molecule is at its isoelectric point, that means it has a charge of 0, and that is 100% of it has a charge of 0. What's also significant and important about this is that this molecule is least soluble. So this is a good place where you could, if you wanted to precipitate a protein, or if you needed to precipitate a protein, you'd adjust a protein or the solution that a protein was in to its isoelectric point. Okay. An important takeaway from this is that this molecule still has charges, but they cancel one another out. This is also known as, and it starts with a Z, it's Zwitter, or it's in its Zwitter ionic form. So this protein or this molecule has multiple charges, but they basically all cancel one another out. Now, here's our kind of rundown of our diprotic and our triprotic amino acids. What we're going to do now is work through looking at titration curves for a couple of different amino acids and doing some calculations. Calculations being, well, what is the isoelectric point for a molecule? And I like to introduce isoelectric point, and then I like to go ahead and try to solve for what an solve for an isoelectric point. Okay, so here are all of our diprotic amino acids. There's our single letter codes, there's our full letter code, or our full names, and our 3-letter codes. When we look at something like, let's go ahead with alanine right here. Alanine, represented by A, is a diprotic amino acid. That diprotic amino acid has its C termini with a pK of 2.35 and its N termini with a pK of 9.87. Now, if I wanted to put together I'm just going to go with kind of a rough depiction. That's my 2.35, and then 2.35, 9.87. Now, if you guys remember from the last time that we met, I had those dashed lines. My x-axis was my OH equivalence. This is 0.5. This is 1.5. Where this part of our titration curve gets absolute steepest, this is going to align with 1.0. And then over here, we got 2.0. Okay, I'm going to draw my other dashed line. My y-axis is my pH. I can go with 1, 2, 3, 4, 5, 6, 7, 10, 11, 12. Okay. Now, my molecule looks like this. 3 plus, there we go, my alpha carbon. That is my molecule when it's fully protonated. My molecule is going to be fully protonated when my charge is, sorry, at the lowest possible pH, and my fully protonated molecule with the lowest possible charge, sorry, my fully protonated molecule at the lowest possible pH is going to have a charge of, well, +1. As soon as I hit my first, as I'm adding some sodium hydroxide, potassium hydroxide, a strong base to this, slowly but surely, I'm going to begin to remove from this molecule this hydrogen from my hydroxide on my carboxylic acid. At some point when I reach my first pKa, I'm going to have 50% of my molecule that looks like this, and then 50% that, well, I'm going to redraw just that part. But that C termini is deprotonated. 50% looks like that, 50% is protonated. Now, if I was right here on my titration curve where I've just drawn this X, my molecule looks like what I've got here. Now, can anyone add to the chat what my overall charge of this single molecule is? Perfect. 0. It's neutral. Okay. And that is going to be this central kind of range here. Well, that molecule is going to have a charge of 0. Okay. Now, as I continue to add more and more base, what eventually is going to happen is my N termini is going to be altered. My N termini is now going to be deprotonated. And that's going to be on the far right-hand side. +1, 0 to -1. So alanine is an amino acid that can have a charge of +1, 0, or -1. Alanine can never have a charge of -2, can never have a charge of +2. My range is -1 to +1. Now, for my pi or my isoelectric point, where another way of looking at this is 100% of my molecule has a charge of 0. How could I get that? Well, if I wanted to draw it, I could use my titration curve and I'd go approximately here. Approximately that spot on my titration curve is where I would find 100% of my molecule with a charge of 0. So would everyone agree that that is in between 2.35 and 9.87, my two pKa values. Okay. So if that's right between them, then what we can do is we can take our PI and say that is our two pKa's. 2.35 plus 9.87 divided by 2. I'm going to pull this up on my calculator. 2.35 plus 9.87 divided by 2, and I get 6.11. That location, that X that I've drawn, yeah, it's approximately 6.11. If I adjusted my pH to exactly 6.11, then 100% of my molecule looks like this. N termini protonated, C termini deprotonated. With that knowledge and awareness that every single diprotic amino acid has basically the same thing going on, all that you have to do to solve for the PI of any diprotic amino acid is add up the two pKa values and divide them by 2. That's all that there is. Now, a fair question is that different from your triprotic amino acids? It is, because you have, well, 3 groups. So I'm going to go ahead and do a triprotic amino acid and the titration curve for a triprotic amino acid. So I'm going to start out with let's go with red ink. Our triprotic amino acid, let's go with lysine. My triprotic amino acid is going to have a titration curve that has 3 horizontal regions. I'll draw those all in. Now, is that the best titration curve I've ever drawn for a triprotic amino acid? Yes, it is. It's the best one I've ever drawn. Lysine, K, okay. The way that it's depicted right here on the far left-hand side, or that I just had circled, what you might notice is the N termini is protonated, the R group is protonated, and the C termini is deprotonated. So at the lowest possible pH, what is our charge for lysine? Well, it's +2. So then what I've got is I'm going to highlight my lysine R groups over here, or sorry, my lysine pKa values. I've got a pKa of 2.18, 8.95, 10.53. I am most interested in looking at those pKa values in a increasing sequence. What's the lowest? What's the highest? How do we get between those? The next thing that I want to do is I want to go ahead and kind of draw my little dots corresponding to my pKa values. Now I'm going to go over, I'm going to pick a different color. So I'm going to draw my dashed lines. When lysine is fully protonated, there's a +2 charge. So to the left of my first dashed line, that's where that's going to be, at +2. Now, the next step, we're kind of making a number line here. When we deprotonate one group, that molecule is going to go from a +2 charge to a +1 charge. And so That's going to be the number that is between our next dashed lines. Then when we deprotonate our next group, that molecule is going to have a charge of 0. Then when we deprotonate our next group, which we have 3 ionizable groups, this is going to have a charge of -1. Now, keep in mind, was this right here where I just drew a star, where my molecule was a +2 charge, was that at a low pH or a high pH? A very low pH, a very acidic environment. We know that that low pH was below our lowest pKa, 2.18. So what I'm going to do is I'm going to say, all right, well, 2.18. I like to draw a little number line like this. Now, one of the things that I want you to feel comfortable with is I haven't drawn any structures. That's because I don't really need to. Because I know what it looks like in an extreme where it's fully protonated, and then I know it's a triprotic amino acid. So there are 3 groups that can be deprotonated. So the next group is going to be have a pKa of 8.95. The last group is 10.53. Okay. Now, with this information, what's important to be able to do is to say, all right, well, what's my PI for this amino acid? We know that our PI is where 100% of our molecule has a charge of 0. So which two, or we only need 2 pKa values to find where 100% of our molecule has this charge right here. That would be 8.95 and 10.53. We add those two up and we divide it by 2. 8.95 plus 10.53 divided by 2, 9.74. Okay, wonderful. Now, this is something that what people have a tendency to get caught up on is when they see a triprotic amino acid, they think, oh, well, I'm calculating PI, I just need to use all my pKa values and divide. Nope. There are certain pKa values that matter more than others. And the ones that matter are the ones that get you to land where your molecule has, or 100% of your molecule has a charge of 0. Now, aspartic acid is a triprotic amino acid. Lysine is a triprotic amino acid. We just did lysine, but all that you have to do is get to a point where you understand what are the extremes of that molecule's charge. So let's do aspartic acid and look at this form of the molecule. The way that it's drawn right here, what is the charge of it? +1. If we deprotonate a group, it's going to be 0. Next group, going to be -1. Next group, -2. Triprotic amino acid, those 3 ionizable groups. Okay? What we need to know are what are the pKa's that are here and here. How do we answer that question? Well, we remember that this form corresponds to the +1. That is our most acidic form of our molecule. So now we go back and look at our pKa values. Aspartic acid has 3 pKa values: 2.10, 3.86, 9.82. Okay, jump back over here. We're going to go with Which pKa value goes right here? Is it the is it the lowest or the highest? The 2.10. Absolutely. So we got 2.10. Then we follow that with 3.86. If my question is what is the PI of this amino acid, I don't need to worry about this pKa value right here. I don't care about that. All that I care about are these two, 2.10 and 3.86. Add those two up, divide by 2. So our PI for aspartic acid is going to be something like 2.95, roughly. Okay. Now we'll go ahead and jog ahead a little bit to talk about peptides. A peptide's formation. Now, here what we have is the general structure of peptide bond formation. We've got the N termini and the C termini, the N termini and C termini. The N termini of one amino acid is going to react with the C termini of another amino acid. And in the process, we're going to form a peptide bond. A peptide bond is a very strong covalent bond. And when that covalent bond is formed, we are going to release, in addition to a peptide that is elongating, we're going to release water. So here are two reacting amino acids, and I've drawn them a little bit differently. And the reason is because there's there are some places that you look at amino acids and it's like they're drawn by organic chemists as opposed to biochemists, because this is what the molecule is going to look like at a physiological pH. So you're going to have a protonated N termini and a deprotonated C termini. So that's why I drew it that way. Okay. And basically, these two hydrogens are going to react and take that oxygen, and boom, we're going to release water. Okay. Next up is looking at a peptide and calculating how a peptide can change, calculating the charge, calculating the PI. We are going to look at the possible charges that this peptide can have. Okay, so we have Y and E. And I've got some video examples of this sort of problem on my YouTube channel that I'll add to the page, or I'll add to our Canvas page. So our N-terminal amino acid is tyrosine, represented here by the Y. Our C-terminal residue is this glutamic acid. Now, when it comes to calculating the overall charge of this molecule, this is the fully protonated form of the molecule. Could somebody add to the chat what the overall charge of this molecule is? +1. You're absolutely right. Okay. Now, when we look at these two, Y and E, okay, the pKa for the N termini of Y is about 9.11. Okay. The R group for tyrosine is 10.07. The C termini is 2.20. Do we need that C termini or C terminal pKa value? Let's see, where's our C termini of that amino acid? It's right here. So is that group ionizable? Has that group changed? It has. It's pretty fundamentally changed. So that 2.20, that's not something that we worry about anymore because that group is no longer an ionizable group because it's a part of my peptide bond. So too is the N termini of my next amino acid. And these are all labeled. So the pKa of N, the C, and the R group. The pKa of the N termini of this glutamic acid with a 9.47. That's a part of my peptide bond, so I don't care about that. Then my R group, 4.07. And last but not least, the C termini of my glutamic acid is 2.10. Okay, so this molecule can have, we've already established that this has a +1 charge. How many ionizable groups do we still have? 4 is our correct answer. We've got our two R groups and then our N termini and our C termini. So we've got 4. So we've determined that this molecule, the most positive it can be is +1. Then we're going to deprotonate a group. I'm going to switch colors to go with, let's go with green. This is going to be first. That's going to be first because, well, that's our lowest pKa. The 4.07 is going to be second. And the only reason it's going to be second is because that's the next lowest pKa. Has nothing to do with it being an R group or anything like that. It just has to do with the magnitude of that pKa. Third is going to be the N termini of my dipeptide. And fourth, final, is going to be the R group of my tyrosine. So now I'm going to switch colors back to red. When I deprotonate my first group, my molecule is going to have a charge of 0. Then we're going to go to -1. Then we're going to go to -2. Last but not least, -3. I stopped there. Would anyone care to say why I stopped at -3? That wasn't a very good plan on me to give you a lengthy question to respond to there. It's 4 ionizations. You're absolutely right. So if I line these up, 2.10, 4.07, 10.07, 9 point, or oopsies, Joel, 9.11, 10.07. If I wanted to calculate the PI, well, it's going to be between those two. 2.10, 4.07. Divided by 2, and we're done. Now, this is essentially what we need to do whenever you're asked to calculate the PI or the possible charges of a molecule. What possible charges can a molecule have? Could this peptide right here ever have a charge of -4? Could it ever be +2? No. Which one of these amino acids is my N-terminal amino acid? Is it the Y or the E? Well, N-terminal is going to be the Y. Okay. Now I've got a poll question right here. We got 76 people in the house. If we can get, or 70, yeah, 76. I'm one of them. Let's see the response to that. I bet we can get 100% correct on this one. No, we can't. Never mind. Okay, question. When calculating the PI, do you just look at the numbers between? Yep, that's all there is to it. I bet we can get 100% of the people to respond on this one, though. 10 people left, 9, 8, 7. Can we get 5 more people? 4 more. two. We got two people, but I'm just going to keep talking for a second. So no matter how long an amino or how long a peptide is, if it's 150 amino acids, if it's 112, if it's three amino acids, all that you need to do is basically make a number line like this. What are the possible charges? How many ionizable groups do we have? And then just list them out from your lowest to your highest. Notice how in my number lines, I always started with a positive number because of the fact that, well, I was looking at my molecule with a positive, sorry, in the most acidic environment. Okay. Okay, so do you mind explaining the number of ionizable groups again? Absolutely. Okay, so whenever I'm looking at just a second, I'm going to jump back a little bit. Let's look at, no, that's lysine. We already did that. Um, Tyrosine. Here we go. So one thing that I want you guys to know is that I will always give you the pKa values. I will give you every pKa value that you need for these sorts of calculations. So if I asked for the PI of tyrosine right here, well, what I would want you to do is I would want you to say, okay, do I remember the single letter code for tyrosine? Yes, I do. It is Y. Okay. Now, do I remember the structure of tyrosine? I've got a pretty good idea of what it is. I'm here what we have. Here is that picture. This molecule right here has a charge of +1. Now, for right now, as you're working through these sorts of problems on your exam, it's going to be a little bit different. But as we're working through these, what we're going to do is we're going to see, all right, well, I have three groups. I have a pKa that's labeled NH3. That's going to be my N termini. I also have a pKa that's labeled COOH. Every single amino acid will have those two pKa values because every single amino acid has an N termini and a C termini. So every single amino acid has those two ionizable groups. Some amino acids, including tyrosine, arginine, lysine, histidine, aspartic acid, glutamic acid, and cysteine, all have a third ionizable group. That's its R group. This hydroxyl group right here is an ionizable group. So tyrosine can effectively lose that hydrogen, and rather than having a hydrogen there, will have a negative charge. So those are my three ionizable groups. So it has to do with looking at and becoming familiar with those amino acids and understanding how they can change. Now, with that, when you're looking at a single amino acid, that's kind of all that it boils down to. But let's say that we looked at a amino acid or let's go with I can go with a tripeptide. DRY. Dry. That means I have my N-terminal amino acid is aspartic acid. My middle amino acid is arginine. And my third amino acid is tyrosine. Now, what does this molecule look like? Okay, well, for starters, I've got this amino acid here shown on the right-hand side of my screen as my C-terminal peptide, or C-terminal amino acid. This right here is aspartic acid. That is my N-terminal amino acid. And then, where do I have an arginine? My last one in the middle is this guy right here. Now, it's not so much important that you recall those structures, but instead that you can classify them. Okay, these are all triprotic amino acids. Aspartic acid is a polar negative residue, whereas arginine is a polar positive, and tyrosine is a polar uncharged residue. Now, what I like to do whenever I'm doing this sort of thing is I like to think about here's D, here's the R, here's the Y. Okay. Now, what I know about this is I know that I'm going to draw this little box around them. I know that I need to be familiar with the N termini of my aspartic acid. So I'm going to write my N-terminal pKa value to the left of that capital D. So I'm going to write that 9.82 because that group is ionizable. I also know that the N-termini of an amino acid or a peptide is going to have a positive charge. So I'm going to label positive and I'm going to write my pKa. Then I'm going to look at my R group. My R group for aspartic acid, when that is fully protonated, which is what I see right here, when this group right here is fully protonated, it has no charge whatsoever. So now, since I'm looking at DRY and trying to visualize this as a fully protonated molecule, I'm going to label that as 0 because it has no charge. It's neutral. It's 7:51, so if anyone wants to leave, I hope you have a great evening. I'm going to finish this up, though. I don't want you guys to feel obligated to stay. I'm just going to answer this. So I hope you have a great evening, and thanks for coming to class. I'll be around to answer some questions, though. So I'm going to continue on with this, though. Um, arginine. Arginine is a polar positive residue. So when that is fully protonated, it is going to have a positive charge. Now I'm also going to write my pKa values for the 3.86 and arginine, which is 12.48, and tyrosine. Okay, now I'm moving on to tyrosine. Tyrosine, when it is fully protonated, also has a charge of 0. And that R group for tyrosine is 10.07. Last but not least is my C termini of tyrosine, which is, well, it's a carboxyl group. When a carboxyl group is fully protonated, has no charge whatsoever, and it gets a 2.20 pKa. Okay. So now what's important to do is to kind of go back. I drew this little box around my letters because these are the amino acid, or these are the groups that I care about. The ones that I don't care about are, and I'm going to switch colors here. I don't care about the C termini of my aspartic acid because that is wrapped up in my peptide bond that connects aspartic acid to arginine. Now bringing me to arginine. I don't care about the N termini of arginine, the 9.04, because that is now a part of a peptide bond. So as soon as a peptide bond is formed between two amino acids, I don't care about that group any longer. The C termini of arginine, the 2.01, well, that right here, also in a peptide bond, so I don't care. The N termini of tyrosine, the 9.11 right here, I don't care about that. So I've accounted for all of the pKa values that I care about in this calculation. And now what I need to do is I need to come up with what is my overall charge of this molecule. Well, I've got this positive and this positive. So this molecule can have a charge of +2. Could this molecule have a charge of +3? Nope. It can be part of +2, and that's kind of how extreme it can go. Then, when I deprotonate it, well, that means I'm going to lose a proton. In that group right here, the one with the lowest pKa is going to be the group that loses that proton. And whenever one proton is lost, my molecule is going to have a charge of +1. Then I'm going to deprotonate again, going from +1 to 0. And that's where this 3.86 is. So I'm going to be kind of keeping tabs on this. So I'm going to write 2.20. 3.86 minus 1. And now my next lowest pKa value is 9.82. Then minus 2. My next lowest pKa is 10.07. And then last but not least, that minus 3, that 10.07, and finally 12.48. So this molecule, and this is one of the questions that I like to ask, what are the possible charges of this molecule? This molecule could be +2, or it could be as extreme as -3. It's never going to be +3. It's never going to be -4. +2 to -3, and everything in between there. Now, so to answer that direct question, how do I determine the number of ionizable groups? Well, I identify the amino acids at play, and then I identify, are any of those groups involved in a peptide bond? If it's in a peptide bond, I don't care about it. Now I've got this. I could solve for my pi. It's going to be 3.86 plus 9.82 divided by 2. That's like 13. I'm going to call it 6.65 or something like that. I don't know the exact number, but roughly there. Okay, next. The ones you don't care about. So, did I see another question? The ones you don't care about are the ones that are being used. Yeah, okay. Sorry for the extremely lengthy answer to a fairly discrete question. Any other? Oh, we did it. We got to 75 out of 75. So one bonus point on the first exam. I'm not sure when that last one rolled in, but I don't think I have ever given 13 minutes and 1 second on a Zoom poll question, but it's first time for everything. So, okay. So I'm gonna make a note to that. Um, what was the possible charges of the molecule? This one could be that specific molecule, DRY, could be +2, could be +1, 0, -1, -2, -3. No worries. No need to apologize. Okay. I think that covers everything that I wanted to cover and then some. So I feel good about that. Like I said, I'll put some videos up where I walk through similar sort of calculations. Since you are looking for when the molecule goes from -1 to 0, you only need two pKa values. That's absolutely right. You could have 312 pKa values, but only two matter when it comes to calculating your PI. Okay, everyone. I'm going to go ahead and stop my recording, stop my share, and